Welcome to The Explainer. Today, we're going to tackle a classic coding interview problem, one that has a solution that's just deceptively clever. All right, let's dive right in. Picture this. You've got this unsorted array of numbers, right? It's just a total jumble. Your mission, should you choose to accept it, is to find the length of the longest chain of consecutive numbers hiding in that mess. But here's the kicker. You've got to do it fast, like really fast, ideally in just one single super efficient pass.
So you know the first couple of ideas that probably pop into your head are pretty intuitive. They make sense. But they've got a major drawback, and that's performance.
First off, there's brute force, right? For every single number, we could just start checking. Does the next one exist? And then the one after that? You can see how this gets out of hand. It's an O(n)² solution, which is just painfully slow for big inputs. Okay, so a better idea would be to sort the array first. That gets us down to O(n) log n, which is a huge improvement for sure. But here's the thing. A good interviewer is going to look at you and say, can you do better?
Yeah, so that's the crucial point, isn't it? We have to think past these obvious kind of clunky paths. The real goal here, the top-tier solution, is to get this done in linear time, O of n. But how on earth do you do that without sorting the thing first? Okay, this brings us to the core insight, the aha moment that really unlocks this whole thing. See, the biggest problem with those slower methods is just a ton of wasted, repetitive work.
I mean, just think about it for a sec. If your array has, say, the numbers 2, 3, and 4, why in the world would you ever start counting from 3 or from 4? You already know they're just part of a longer chain that started earlier. It's like you're just redoing work you don't need to do. And this is where a really simple analogy makes it all click. Trying to count from every single number, that's like trying to find the longest train on the tracks by walking up to every single car and starting your count from there. Which is just silly, right? Because what you really need to do is just find the engine, and that's it. That perfectly illustrates the solution. We don't need to check every car. We only need to find the engine of each potential sequence and then start counting. So let's give these engines a name. We'll call them sequence starts. And the rule is super simple. A number is a sequence start if the number right before it, so num minus 1, is not in our set of numbers. That's the whole definition. And honestly, this little snippet of code you see here, this is everything. This is the entire trick boiled down to one simple check. It's how we find our engine before we even think about starting the count. This is the key to getting rid of all that wasted effort.
All right, so let's put this into practice. Let's walk through exactly how this clever little idea actually works, step by step.
The process is actually surprisingly simple. First thing you do, dump all the numbers into a hash set. Why? Because that gives us those lightning-fast O(1) lookups. We can check if a number exists like instantly. Then we just loop through our numbers again, and for each one, we do that magic check. Is this a sequence start? If the answer is yes, and only if it's yes, do we start counting up to see how long that chain is. And the whole time we just keep a little variable on the side to track the longest one we've found.
Okay, let's trace this with a real example to see it in action. Our input array is going to be 100, 4, 200, 1, 3, and 2. Okay, we start our loop. First number up is 100. We ask, is 99 in our set? Nope, so 100 is a sequence start. We check for 101, it's not there, so the sequence is just length 1. Our max length so far is 1, easy enough. Next up is 4. Is 3 in our set? Uh-oh, yeah, it is, so we just skip it. It's not an engine. Then we get to 200. Is 199 in the set? No, so 200 is another start. We check for 201, it's not there. Length is 1. Our max is still 1. But now we get to the number 1. We ask the question, is 0 in our set? No, it's not. And bingo, we've found a real sequence start. Now the fun begins. We actually get to do some counting. So starting from 1, we look for the next number. Is 2 in the set? Yep, length is now 2. How about 3? Yes, it is. Length is 3. What about 4? Yep, that's in there too. Length is now 4. So we check for 5, and nope. It's not in the set. The sequence breaks right there, so we stop counting. So that gives us a sequence length of 4. That becomes our new maximum length. And, we'd go on to check the last couple numbers in the array, but nothing is going to beat that. So 4 is our final answer.
Okay, but here it is. The most important question. The one you'll always get asked. Why is this so fast? I mean, at first glance, you see a loop inside another loop, and your brain just screams, O(n)², right? But it's not.
The magic here is that the inner loop and the outer loop aren't really nested in the way you'd think. They don't compound their work. Look, the outer loop is going to touch every single number once. That's clear. But the inner while loop, the counting part, that only ever kicks off for numbers that are the start of a sequence. So think about it. Any given number in the array is visited at most twice. Once by the outer loop, and then maybe, just maybe once more, by an inner loop if it's part of a chain being counted. And that's the secret. That's what keeps the total number of operations linear and gives us that beautiful, efficient O of n complexity.
You know, a great algorithm isn't just fast, it's also robust. It has to handle all the weird, tricky edge cases you can throw at it. So let's really quick see how our logic holds up.
So what if you get an empty array? Well, the loop never runs, and we just return 0. Perfect. What about duplicates? The HashSet takes care of that for us, completely elegantly. It only stores unique values, so we don't have to worry. Negative numbers? Not a problem at all. The logic works exactly the same way. And what if you have an array with no consecutive numbers, like 100, 200, 300? Well, in that case, every single number is its own sequence start of length 1, and our code correctly figures out that the max length is 1. See? It just works.
So, here's the big takeaway. It's not just about this one problem. It's about recognizing a powerful, reusable pattern. This idea of finding the true beginning of a subproblem so you can avoid all that redundant work, that's a technique you can use to optimize all kinds of algorithms. It is an absolute superpower to have in your coding toolkit. So the real question is, where else could you use it?